All right, we need more examples. So in these next few examples, we're going to be applying integration rules, but we're also going to get a little bit clever. You know, I like to get clever with algebra. We did this back with, when we first started doing derivatives. I showed you how you can do some clever algebraic manipulation to sort of simplify something and make it doable with the basic rules that we already know. So, for example, put a dx on the end of that. There we go. There is an integral problem, or an antiderivative problem. Okay, it's an indefinite integral that on the surface looks like something we don't know how to solve. Remember, I mentioned that the power, the product and quotient rules, we're not going to go over analogs of those in this class, right? You'll learn sort of like an integration version of the product rule next week. So, how can we possibly do this then, right? If it's a quotient, well, the answer is you can just do some algebraic simplification on it. Let's distribute the division by the square root of x. So x over the square root of x plus 1 over the square root of x dx. We have that. Then each of these can be simplified into a power function, right? First of all, let's write the square root as a power. So this is x to the 1 over x to the power 1/2 plus 1 over x to the power 1/2. And now we can just rewrite these each individually as power functions. For the first term here, we can use the rule that says, hey, subtract the powers, 1 minus 1/2, right? So this is going to be the integral of x to the power 1/2, and then plus, if the reciprocal of x to the 1/2 is x to the power negative 1/2. And there we go. So we took what looked like a complicated function, a complicated quotient, and we just simplified it into a sum of two power functions. Those are easy because you just do the inverse power rule on each of them. So here's how we apply the inverse power rule. First one, instead of to the power 1/2, we're going to take that power 1/2 and we're going to increase it by 1. So 1/2 plus 1 is 3/2. Then you divide by that number. So x to the power 3/2 divided by 3/2. For the second term, x to the power, we're going to take negative 1/2 and add 1, which brings us up to positive 1/2. Okay, negative 1/2 plus 1 is positive 1/2, and then we'll divide by 1/2. And then we'll throw a plus c on the end. And we got it. We should simplify it a little bit, I think. Personally, I would prefer to see this, instead of dividing by these fractions, I would prefer to just multiply by the reciprocals of those fractions, and you can skip straight to that result if you're comfortable with that, which I hope you are. And write it like that. But that seems fine. That seems like a great answer. I wouldn't feel the need to do any more manipulation to it beyond that. So there's one example. Let's look at another one. Let's look at the integral of e to the power x plus 2 dx. Okay, on the surface, that is a composition of functions. Now, I did tell you that we are going to learn an integration rule for a composition of functions. Okay, so potentially. Like this is sort of like an inverse of the chain rule. It's called integration by substitution. But we don't actually need that here. And the reason we don't need that here is because we can instead leverage some properties of exponents. So remember that when you have two powers added together, when you have a sum of two things in the power here, then that could have been two separate exponential expressions with the same base and different powers. Right? In other words, remember how when you multiply exponential expressions with the same base, you can combine them and add the powers together? Here, we're going to take the combined version and we're going to pull it apart into 2. So let's call this e to the x times e to the power 2. Right? See how that is the same as that? And now e squared is just a constant. So that constant can factor out. We can remove that constant from the integral and get that. Okay? So we're using the constant multiple rule there. Now e to the x, its antiderivative is itself. So now we have e squared times e to the x, and then of course plus c. And here we can then combine this back together again if you want into e to the power x plus 2 plus c, which is our answer. So the antiderivative of e to the x plus 2 is itself plus an arbitrary constant. 3. Let's do the integral of sine of x divided by cosine squared of x. All right. This problem is almost easier now than it is going to be later, because once you've learned other integration techniques, you're going to be tempted to apply all these complicated strategies. And I see this a lot in like multivariable calculus or Calc 2. Like students in those classes, they know all these complicated strategies, and they see something like this and they think, ooh, that looks complicated. I need to do something complicated. But in fact, you can actually solve this problem in a super, super easy way by just manipulating it around with a little bit of trigonometry. So let's see. I'm going to split this out into 1 over cosine of x times sine of x over cosine x. That's the same, right? Because cosine squared comes from cosine times cosine, and then the numerator would be 1 times sine, which is just sine. Right? So all agreed that's the same thing, right? But then 1 over cosine is secant, and sine over cosine is tangent. Secant x times tangent x. What is that the derivative of? It's the derivative of secant of x. So this is, an antiderivative for this is secant of x plus a constant, right? So this is just recognizing a differentiation rule in reverse. Number 17 here is the derivative of secant x is secant x times tangent of x. So the antiderivative of secant times tangent is secant plus a constant. So there you go. So there's a few examples of how you can use the basic differentiation rules along with some clever algebra, exponential rules or trigonometry to help you find answers more easily without having to apply any complicated rules.